I would like first to thank the committee of organization of this conference for having me here today. So, just begin with a short introduction of myself. I am the head of one of the 6 divisions at INRS. The research activity at INRS is divided in 6 divisions, which will perform, explore specific fields on occupational and safety and health. And alongside the division of occupational epidemiology, okay, yeah, I have this, okay. Alongside the division of occupational epidemiology, working life, work equipment engineering, process engineering, pollutant metrology, my division, toxicology and biomonitoring division, conduct research in industrial toxicology. That means that in our division, we will perform research to assess the toxicity of chemicals, mainly of chemicals at workplace, but also to evaluate the risk associated with those exposure. So as such, in my division, we cover different fields of work, including cancerology, reprotoxicology, immunotoxicology, neuro and ototoxicity, dermal absorption, and the last one is the biomonitoring. In the direct line of one of the theme of this conference today, I'll give a talk on the advanced technique for hazard and exposure assessment on occupational field. We already have today some really nice presentation on this topic. So my presentation can be viewed as sort of summary of all those new techniques. So I'll just start with a short introduction on a risk assessment, human risk assessment. It will be just to set the scene of my presentation, would be around the assessment of the exposure to a mixture. And then I'll discuss some advanced technique for both exposure and hazard assessment. And just before getting to the heart of the matter, I just would like to point out that I will not really go into depth on each topic, but it will just be this kind of overview. Okay. Conducting a risk assessment for human means that the principal objective, the aims, will be to answer to the question of the extra risk of health problem caused to an exposed population. So the 4-step risk assessment process will involve a structured approach, which is summarized in this slide. The first step is the hazard, is the identification, which will try to answer to the question, what are the health problems caused by a pollutant. Then we have the dose response assessment to investigate the level of exposure associated with the health problem we identify. The exposure assessment, of course, how much of the pollutant can we find in the population? Are they specific population or not? And how many population are exposed to these chemicals? And overall, the final step is the risk assessment step, which will combine the finding of all the previous different steps to assess the overall risk of health. So together, there's 4 steps from really a comprehensive framework for assessing and understanding the potential health risk associated with pollutants. However, we all know that human health risk assessment is faced with various challenges. We already discussed also that today, one of the challenges is the growing number of chemicals, new chemicals, novel chemicals entity, for example, nanoparticles, but also chemicals from repurposing or remodeling of existing chemicals. I think tomorrow there will be a presentation on microplastic. And other contaminants of emerging concern, such as the climate change-related new pollutants, such as mycotoxins. And yet the complexity does not stop there. Many of these chemicals are still unknown, and it is clearly admitted that human is exposed on a daily basis to a mixture of chemicals. We can try to define a mixture as any combination of two or more chemicals that may, and that is really important, jointly contribute to real or potential effect, regardless of the source of exposure, the spatial or the temporal proximity of this exposure. A simple mixture is defined as a mixture whose components are fully chemically characterized. That means a group of chemicals, for example, a pesticide formulation, while in contrast, a complex mixture is really a mixture in which, for which not all constitutions are characterized. The combined exposure to multiple chemicals of human and the mixture risk assessment and management have received this last year increasing interest, as evidenced by a large number of research projects, one of them being the research project PARC. And what about PEROSH? PEROSH is no exception in this content. We know that workers are exposed to multiple, to mixture, mainly to complex mixture when in their work environment. One example is the worker from the waste plant, for when treating the waste management, that can be exposed. And also today there was a talk on the combined exposure to chemicals and biological agents in this workplace. So an occupational risk assessment for workers finds itself at a crossroad where there is a need to characterize the chemical composition, also an imperative need to evaluate and to gauge their toxicity. That means that a high level of information is needed about the chemical exposure, the toxicity, and the mixture effect. First of all, we should have data on the chemical characterization, on the exposure. That means that we should identify the chemical in the mixture and also measure those chemicals. Toxicological characterization is also important to identify the adverse effects of these chemicals, but also to identify the driver of the toxicity. Because the question here is one or several substances accountable for the toxicity? Because the ultimate goal when performing risk assessment is the risk management. And to perform the risk management, we should know what are the drivers of the toxicity. Traditional approach for risk assessment have proven well adapted for the individual chemicals and specific scenario, but as our understanding of mixture exposure evolves, this traditional approach proved inadequate for mixture exposure. Although those information is not really new, we all knew of those observations, but they are becoming increasingly important and they have fueled recent development both in chemical and toxicological characterization of mixture. So with the frame of PEROSH in mind, I'll just now provide an overview of some selected recent progress. And I'll first discuss the advanced technique for the exposure assessment of a mixture. The innovation have occurred in the field of identification, measurement, but also in the field of sampling. And one particular innovative approach I would like to discuss today is the use of silicone wristband. There are up, I think I can just, okay. Those are the silicone wristband. The silicone wristband as you are used as personal exposure devices. They offer several distinctive advantages. They are non-invasive, easy to collect. They are able to offer a comprehensive assessment of both inhalation and dermal exposure. And also what is really remarkable about silicone wristband is their ability to capture a diverse area of chemicals. This makes them really suitable for a wide range of application, whether using a targeted analysis method or a non-targeted analysis method. And the validity of this technique has been established via comparison with other more accepted sampling methods, such as air monitoring or hand wipe methods. And just to illustrate here the use of silicone wristband and the power of this technology, here is a recent study from Levasseur et al. They characterized the exposure of firefighters to several chemicals while they were off duty but also on duty. In this study, by using each firefighter off-duty silicone wristband to represent the baseline exposure, they have assessed the occupation-related exposure. The occupation-related exposure is the on-duty exposure while there were a fire or not, or while there were a fire, or no fire. And in this study, they identify several chemicals in those silicone wristbands, including pesticide, PFAS, organophosphorylate flame retardant, brominate flame retardant, PAHs, PCB. And for some of these chemicals, the exposure while on duty was higher than the exposure off duty. This research demonstrates the usefulness, the utility of using silicone wristband to quantify occupational exposure, in this case for firefighters, but also its potential in mixture study. Another advanced technique for exposure assessment is the use of a direct reading sensor. The need to detect hazardous exposure in time to rapidly mitigate harmful effects have led to the development of this sensor. Those are direct reading sensors that can say, sense the presence of a compound, collect a sample, analyze the sample, and even display the result in real time. So those sensors are becoming increasingly versatile, ranging from placeable to wearable sensor devices. So the first really sensor was the pocket radiation dosimeter, which now have been joined by a growing number of different other sensors using various technology. I will not go more into depth on this sensor because tomorrow I think there will be a keynote on the use of this sensor. And this sensor may make the exposure assessment convenient, but one limit of this sensor is that they are mostly specific to one chemicals or one group of chemicals. So when trying to tackle the complexity of a mixture, one strategy may be the use, for example, of a network of wireless sensors to monitor multiple chemicals in real time. And yes, in this afternoon, my colleague from ENRS, Naresh, she's here, have a talk about the use of those network of sensors. However, for the vast majority of chemicals, there is a lack of exposure data, and it is really unrealistic to obtain perfect data for all chemicals. So in Europe, exposure and regulatory risk assessment largely relies in model also. A chemical exposure model for chemical substance, those exposure model, the aim of the exposure model will be the assessment of a substance level at a specific point in time, in a specific medium, for a specific scenario exposure. It's a conceptual or a mathematical representation of the exposure process. And there are a numerous number of exposure models which are available and that have been developed now, depending on their context, their use context, the scope, or the applicability domain. And among them, I think you all know of Stockholm Manager, which is a knowledge-based platform aimed at reducing exposure risk to chemical compounds, but also to biological agents at workplace. The Stockholm Manager consists on several tools, such as control binding, quantitative exposure assessment, and for conducting the risk assessment by combining the hazard information of a product with an estimate of exposure by inhalation or by skin contact. And if risks are identified, control measure can be selected. However, to be really able to use this exposure model in the context of mixture risk assessment, research is still needed to predict the likelihood of the specific co-exposure. So the most likely co-exposure can be considered in the mixture assessment. And for my last example on the advanced technique for exposure assessment, we'll move from external exposure to internal exposure. And I will just talk about non-targeting screening metabolomic approach. The non-targeting screening metabolomic approach is a technique which is based on human biomonitoring. Human biomonitoring consists on measuring a parent chemical or a metabolite or their metabolite in biological fluid, such as blood or urine. Human biomonitoring aggregate exposure across different routes of exposure. So the measurements are used as an exposure biomarkers, and human biomonitoring has really proved to be a valuable tool for inferring chemical exposure. Human biomonitoring may reflect multiple exposure scenario and exposure to multiple compounds. So, the metabolomics. The metabolomics is is part of the omics technology. Here are the metabolomics, and the metabolomics approach will have as principal aim to capture as many metabolites as possible in a single analysis. It is what is called an hypothesis-free approach, as depicted in this picture. When using traditional methods, usually the exposure will consist, the analysis will consist on analyzing known substances, really well-known substances. When using a non-targeting screening approach, this method will provide what is called as fingerprint of the whole metabolite in the biological sample. In this fingerprint, the fingerprint will include most known substance, of course, but mostly unknown substances. Those metabolites can be exposure biomarkers, And then in that case, these techniques, these metabolomics will offer information, provide information on the uptake of chemicals. But also those metabolites can be what's called effect biomarkers. Effect biomarkers are endogenous substances whose changes in concentration level reflect or prove an early effect of the exposure in human. And in this case, the metabolomics will really contribute to the hazard identification. The advance in metabolomics has been closely related to the advance in analytical techniques, but mainly in the progress made in bioinformatic tools for the data processing and also for the metabolite identification, which is still the bottleneck of this approach. However, from my point of view, metabolomics is really a promising approach for mixture exposure assessment, even if it has to be applied in PEROSH yet. And now we'll move to the second part of my presentation, and we'll have a look on recent innovation for hazard assessment. The traditional testing, toxicity testing method is usually based on experimental animals, using many high doses. However, with the global awareness for a safe environment and also the various challenges faced by risk assessment, researchers has really invested in the development of reliable and also relevant approaches for toxicity testing. One such paradigm is called new approach methodology, which will encompass a spectrum of technology, methodology, approach to perform hazard assessments and to provide really a comprehensive information on toxicity, all the while championing the ethical principle of animal welfare. So, the new approach methodology can be usually defined as any technology, methodology, approach, or combination that can provide information on chemical hazard without the use of animals. This approach will allow rapid testing of a larger number of chemicals and consequently also the screening and the prioritization of those chemicals. The key components of NAMs are really wide. Today I will just talk about the in vitro experiment and the in silico approach. Those NAMs are able to provide both mechanistic knowledge but also dose response relation information for the chemicals. So let's have just a look first on in vitro testing. So, in vitro assay aim to predict the toxicity response for different chemicals. And among the different in vitro models available, I think that human cell line models are really as the most relevant model to assess the potential human health risk. These in vitro models offer a unique advantage by providing direct cellular evidence of adverse effect. They allow also the examination, the investigation of various endpoints from oxidative stress, genotoxicity, inflammatory effect, endocrine disruption effect. Today there was a presentation of also hepatotoxicity, for example. So this approach, given that it's a rapid approach, it can generate really abundant bioactivity data, and thus for various key endpoints. So one of the key strengths of using in vitro testing method is the integration of different information across different toxicity endpoints. And this integration will enhance our ability to really comprehensively evaluate the effect of chemicals and provide a more efficient testing strategy for classification, for example. In addition, researcher also has had adapted the existing in vitro assay for studying mixture. The adverse effect of mixture can be tested as component-based approach, which means that the different component of the mixture is tested one by one, or using the whole mixture approach. And this is what is really interesting for the assessment of mixture. So the whole mixture approach means that the mixture itself can be tested. Even if it is an intentional mixture, I already talked about pesticide formulation, but also an unintentional mixture. What is what we are going to face mainly at workplace. When testing an intentional mixture, this allows the consideration of any unknown chemical in the mixture, because we are testing the mixture as a whole, and also this allows the consideration of any interaction among the mixture component. And if the mixture is further characterized, using, for example, the effect direct analysis, that means that the chemical driving the effect in this mixture can be further identified. So now I'll talk about the effect direct analysis. The effect direct analysis type study are really an emerging strategy on profiling on complex samples that will bring together bioassay, biological effect testing by bioassay, sample preparation and fractionation using chromatographic techniques, and the third part is the chemical identification, the identification of the pollutant using the non-targeting screening analysis. Effect direct analysis is just depicted in this diagram. In a EDA analysis, a sample, why not it can be a silico-resistant sample, will undergo in parallel toxicity testing using several health endpoints, and also chemical testing to identify the components which are in this mixture. And to reduce the complexity of the sample can undergo what is called a fractionation. That means that the sample will be separated in several fractions, and then the toxicity testing can be also performed on this fraction. And the third step of effect-directed analysis will be the use of non-targeted screening to identify the chemicals in the different fractions. And the last step will be, also, of course, the confirmation both of the chemicals and of the confirmation also of the toxicological properties. So far, effect-directed analyses are mainly used for environmental toxicology, but I hope that, in a couple of years, we'll see the first study in an occupational safety context for effect-direct analysis. Here is just an example of the use of effect-direct analysis to identify mutagenic and disrupting compound in a surface water. In this example, the authors, Wart and colleagues, have just have analyzed surface water for their yeah, I was looking for that. Yeah, have analyzed surface water for their property of mutagenicity of endocrine disruption, and using the non-targeted screening, they managed to identify two chemicals, the benzotriazole, which is responsible for the mutagenicity, and the androstenedione, which is responsible for the endocrine disruption. The last example for the advanced technique will be the in silico methods. And the in silico method are those alternative approach to generate estimate for chemical toxicity in the absence of data. And I'll just show to you the use of QSAR model, which are mathematical description of biological activity of a group of chemicals in terms of one or more physical property. There are a lot of QSAR models also available. You can find them in the OECD QSAR platform or in Vega platform also. And just this last slide on the work of Lemay et al., who had used combined several QSAR models to prioritize the mycotoxin to further evaluate it for their toxicological property. So in this study, the author has selected 10 QSAR models for the mutagenicity, 6 QSAR models for the carcinogenicity, and the 900 mycotoxins have been tested, and then they managed to identify 95 mycotoxins that are both mutagen and carcinogen. And for these 95 mycotoxins, for 87 of these mycotoxins, there is no data available so far. So this is how QSAR model can also be used for toxicity testing. And for the use of QSAR model for the toxicity, for the testing of mixture, we have now more and more study on this topic, even that more study is really needed, because so far these models are mainly on binary mixture at single concentration. Okay, just to wrap up, in this short presentation, we can see that we have now a lot of tools really available to perform risk assessment to a mixture. Those tools can be for the exposure assessment, for the toxicity assessment, and we can also anticipate that with the growing use of artificial intelligence, we are really going to have more and more innovative possibility for other assessment. So, of course, we still need more research on the occupational fields, because so far, all the examples I show you today are more dedicated to environmental fields. And the last point I just would like to stress out is my last bullet point, is that even if we have a lot of data available, and we are going to have a lot of data available using these methods, those data can stay really useless if they are not really structured. So we need also efforts to enhance the accessibility of the data, their reusability, and also the interoperability of the data. And thank you for your attention.